Hello everybody and welcome to Chapter 8. We'll be starting to look at applications of linear algebra. Our first application will be to linear programming. Our goal in this section is to find the values of the variables x, y that maximize or minimize a linear function, so a function of the type ax plus by, where here a, b, c, all of these are real numbers. But this time we're given constraints. We need all variables are positive, and also that all the points that we're considering fit these inequalities that are linear as well. So under given linear constraints. All right, so let's start with an example. We'll solve this one geometrically, drawing a picture, but in the future what we want is to find an algebraic way of solving these problems. All right, so let's say we're asked to maximize 2x plus y under the given restrictions. We need x and y to be positive, y should be less than 10, x plus y should be less than 15 or equal to, and 4x plus y should be less or equal to 36. All right, so first thing we'll do is we'll sketch the actual region that we're allowed to use. So y equals 10, that's easy, so let's start with that one. I'm going to put it right here. This is y equals 10. So we need to be under this. X plus y is 15. So I have to intercept at 15 on the y-axis and at 15 on the x-axis. So this is x plus y is 15. 4x plus y is 36. That's a bit harder to sketch because I don't have the y intercept would be a 36, which is not in my scale. So what I'll do, I know it hits this point at 9 because 4 times 9 is 36, and I'll find a second point by finding its intersection with, let's say, this one. All right, so intersection. Let's start with that one. X plus y equals 15, and 4x plus y equals 36. We've seen how to solve these using a matrix, so we can do that. I could do row 2 minus 4, row 1 into row 2, 0, 1, 1. So 1 minus 4, that's minus 3. 36 minus 60, that's 20 minus 24, and so I'm getting that y is 8, and then so y is 8, x plus y is 15, which means that x is 7. All right, so 7 and 8. So this point is 7, 8. It's also on our line, so here, sorry, let's try again. On 4x plus y is less equal to 36. All right, so we have all intersection points except for one, so let's find the remaining one. I need to find this one, so red and purple. So this is the first intersection. The second one is at when y equals 10 and x plus y is 15. If I plug 10 in, I'm going to get that x plus 10 is 15, so x is 5. So this point is 5, 10. All right, this is what the region looks like. We're interested in the orange one because we have less than equal for all of them except for x is 0 and y is 0. Now I want to evaluate p at all corners of the allowable region. So let's give them names. Let's say this is A, B is 0, 10, this is C, D, and E is 9, 0. All right, at A, which is 0, 0, P, which is 2x plus y, is 0. At B, which is 0, 10, P, which is 2x plus y, is 10. All right, at C, which is 5, 10, is 20. At D, I'm going to get 14 plus 8, I'm going to get 22. And at the final point, E, I'm getting 18. All right, so we're looking for the maximum. Right now, I only evaluated at 5 different points the function p. Of course, I'm interested in all orange points, and there's no way to actually compute all of these values. But let's see why we should be able to figure out the answer just by looking at the corners. All right, so here I want to sketch the curves on the allowable region. So all the curves are values, fixed values of p. So p equals 0, p equals 5, p equals 15, p equals 18, 22, and 30. I want to see how the function changes and how it behaves. So let's look at the first one. I have 2x plus y is 0. That means y is minus 2x. All right, so we know it hits the axis at 0 and it has slope minus 2. So if it hits here, this is it. All right, so this is p equals 0. Let's try p equals 5. If this is 5, that means that y is minus 2x plus 5. So already you should notice that I'll always get y equals minus 2x plus the value that I'm looking at. So all of these will be lines. So here I'm hitting at 5 and at 5 halves. So this is p equals 5. All right, it's parallel to the blue one. What about p equals 15? I'm getting minus 2x plus 15, so it's going to hit at 15 and at 15 halves. So you can see as I increase the value of p, I'm getting a parallel line that's further out. So here, this one is 18, so 9 and 18, a bit higher. Oh, sorry, this one's bad. So let's start here. Sorry, I'm going to have to move it down. It's a bit off of 9. Yep. And then p equals 22. We know it includes this point. And it will hit at 11. Let me use dark green. So 11 and this point. And it will again be parallel to all of these lines. So this is p equals to 22. And if I go to 30, then it's going to be completely outside our allowable region. All right. Now I'm asked to find the pair in the allowable region which maximizes p. What is the maximum value of p? So let's look at this graph a bit more. You can see that let's write it here, as k grows, the curve p equals k moves further out. So as k grows, we move that way. And so what we're looking at, we're looking for the last k that touches the region. And you can see it happens right here. As I move further out, that will be the last point that touches, the last curve that touches the region will be p equals 22, and it's going to happen at that point. So the biggest k for which p equals k touches our region is at, so that point, let's look back, that was D7, 8. And so the maximum value of p is 22 when x is 7 and y is 8. All right, so the point that we're trying to see is that whenever you have a linear function like this, your curves are going to be super simple. They're going to be parallel curves that move in one direction and move further out as k increases. And so you're looking for the last point at intersect. That will always happen at a corner. However you place your line, the last one is going to be at a corner. And so that's the takeaway here. The function p is maximum at one of the corners of the allowable region, which is why when you're trying to solve a problem like this graphically, it is enough to consider, like we did in B, it is enough to consider the corners of your region and to evaluate p there. You don't have to consider the interior, that won't affect it. You don't have to consider the lines. The corners are the important thing. Knowing the values at the, in this case, 5 corners will give us what the maximum is and where it's happening.